welcome you all to the first session of the day. We have Martin Haye doing Super-Mon, a set of fancy extensions to the Apple II system monitor. Thanks, Martin.
So I'm actually not going to use weakness point today. This is mostly a demo of Super-Mon rather than talking about Super-Mon. So the 5-minute recap of Super-Mon from last year is programming should be fun. We all know this. Basic is kind of fun because it's immediate. You type something in, you type run, and bam, something happens. You do that. Basic is not so fun because it's so darn slow. And B, it's not very powerful. You can't write an arcade game in Basic, really. You can try. Assembly language has some fun aspects in that it's really powerful and really fast. But that cycle of load assembler, edit, change program, assemble, wait, quit, run program, crash, load assembler, start again, is so tedious. It just drags. So the idea of Super-Mon is to try to get some of the interactive quality of basic programming together with some of the tedium elimination, labels and stuff like that from the assembly. Originally, Super-Mon was going to be my HackFest project from last year. I had this crazy notion that I would be able to write the whole thing.
Did you do that
during HackFest from scratch, and that was insane. It actually took months and months of a lot of tweaking and stuff. However, Super-Mon was bootstrapped. I started with this Apple II Plus and a DOS 3.3 System Master and nothing else. And started hacking the original system monitor. So I added a little feature, and then that added a little power so that the next feature I added would be a little bit easier. And I just kind of bootstrapped it that way until I built up Super-Mon to the point where it was really usable. And then I used Super-Mon to write NakedOS. And then I married the two together so that Super-Mon was no longer dependent on DOS 3.3. And then I threw away the system master. Put it back in its attic. So here's what Super-Mon looks like when it boots. Of course, we've got NakedOS prompt and then Super-Mon. And you can access that at any time. And the help system loads itself into the language card just like Super-Mon. So you still have all lower 48K free programs. So today, I'm just going to take you through writing a little program so you can see how it works. I'll talk about some of the features, not all of the features of Super-Mon as we go through this. So first of all, Super-Mon has labels. So for instance, if you go and list part of the built-in ROM, you'll see that Super-Mon comes with some labels built in. So this is the plot routine that you'll see referenced in your Apple II reference manual at F800. It'll also translate zero-page locations if it can figure them out based on the labels you've given it. Now, curse v plus 1, location 26, is actually some other pointer. We should give it a name. So we could call it gr pointer equals 26. Now if we list, Super-Mon is correctly calling it gr pointer. So it's kind of fun, if for nothing else, just to use Super-Mon to kind of disassemble code that you've never seen before, and once you figure something out, you assign that thing a label, and then the next time you list it, it's a little bit easier for you to figure it out, and then you kind of build up an understanding of some other unknown code. So that's one reason why I am using Super-Mon this week to crack wizardry, because it's really handy for that aspect. So you can assign labels, you can list out the labels that you have. Oops, that's a dump memory. Oh, ASCII alongside the dump, just like the GS dump, which is can be nice.
Did you just have to hit reset this abort the dump?
Yes. So here are all the labels that come with Super-Mon, and these are just copied straight out of the Apple II reference manual. So you get to start with those. There's also some zero-page labels. So the T command is the table dump, and it'll dump labels anywhere. It can also be useful when you're disassembling somebody else's code to figure out where are all the places they used this variable. Because once you find some really important variable, you really want to know where they used it. So you have to do two things. One is you need to tell Super-Mon where in memory the program is that you're concerned with, so that it won't search all of them. You do that using the P command. So I'm going to specify the range F800 to FFFF, which is, Wozniak's monitor ROM, and P, I'm telling it that's my program area. Now that's the variable search, and then here are all the places in there that this address GR pointer is used. All right. Enough about disassembling other people's code. Let's actually make some code.
That's the PST.
Pardon?
PST over
I think it's for those letter labels.
-P F814-F F816-P.
Oh. Yes. Okay. I forgot about those. Now this is, I really debated long and hard about this feature because it really makes the monitor look radically different. But it's so damn convenient that I had to put it in. So when you do a disassembly, Super-Mon adds a letter beside each address. And you can later refer to those letters just by using dash. So dash P list will list starting at F80E. And likewise, when you're assembling code, you can branch to dash P or something. The reason I did that was because I kept typing the wrong address over here. Because you type up those addresses all day, and at about 2 a.m., you start typing the wrong address. You start overwriting your own code, and you get really angry.
Can you use those letter labels for anything? Like to assign new values, to assign, in any context in which you would have typed the actual address.
Sure. So if I want to overwrite the plot routine, I can start at -G. I don't know. So now the plot routine will just print the letter A.
no H.
So -G go is the letter A, which is the same as F800 go, which is the same as, this will look really weird, plot go.
Because plot is still assigned to that.
Because plot is a label also, so we'll assign to that. Obviously, the disassembly letters are only there until the next time you do disassembly. Now -G is somewhere else. So it just helps you reference the things that you can see on the screen right now.
So by the fact that you're never going to have, I guess you're never going to have more than 26 lines on the screen at one time.
Very convenient that there are just that many letters that that aren't A through F.
Right.
When I discovered that, I was like, oh, even better. Okay, so let's write a little program. I'll put it down at at 2000. So I'm defining a new program area. Here's what's there right now, nothing. I guess we might as well start with hello world. So first of all, strings in assembly language obviously are not like strings of basic. You gotta put them somewhere. So I'll put a string at 2100. So this is just going to put the ASCII codes for hello KFest followed by 8B, which is return, followed by 0. Dump out that area of memory, you can see that I just put it there. Okay, so now let's write a routine to print it out. In assembly language, you use either the X register or the Y register to count things. So we'll start at 0 and we'll count up. Let's add a label to our string. Since we put it at 2100. So I'm going to load the accumulator from that buffer.
You have to put in a space after the beat to indicate that you're giving it a mnemonic rather than a numeric output.
Right. So for instance, if I did this instead without a space, I can just start typing out codes.
Right.
That's something. Yeah. So that in general, the space means I want to put in I want to assemble something. Anyway, so we'll get the next character. We'll output it. So we'll jump to the subroutine character out, which is up in the ROM. We'll increment the counter, and we'll jump to the beginning of our loop. Here's a nice use for the dash labels. You can see the dash H is the beginning of the loop. And you don't have to type out G02. Okay, well let's see how that goes.
You didn't stop the counter. You didn't have to why.
Right. We went past the end of the buffer. So we actually need, so I stuck that 0 at the end with this thought in mind. So we need to put a check. Before we print it out, we need to put in a check that if it's 0, we need to stop. So instead of overriding all that code,
because when you enter a string that way, it automatically terminates at 0?
No, he added.
Oh, I didn't see
I
that.
added a 0 explicitly.
Even though it was filled with zeros.
Yeah.
It was already filled with 0, so it was kind of unnecessary. So here's something you can't do in the monitor. I want to insert something at just before 2005. So what Super-Mon just did is it pushed the stuff that was at 2005 down, like 64 bytes. Here it is, down, 32 bytes down. So it gave us some breathing room to add some new code. So we want to compare the A register with 0. If it's not 0, we want to continue with our other stuff. But I don't know exactly, I don't remember where that is.
Dash J, and then you need a
But it's way down, it's like 2023 or something now. So I'm just going to punt and put star here. And we'll fix it later. But if it is 0, I just want to return from subroutine. Dash GL is a nice shorthand for just list the last thing you listed again. So there's that. So now we need to close up that gap above zeros and get the rest of our code back. So starting at line L, I want K is the close operator, and just looks for a series of 0 bytes, finds the code after it, and pulls it back up.
Now, it's just moving bytes. It's not like trying to it's not trying to relocate.
It is trying to relocate. Any branches across that gap will be adjusted.
Oh, really?
Any jumps into the code that's moving will be changed.
This is why it wasn't completed last year.
Yeah, so it is actually relocating.
Can you code in a, what do you call it, structured manner?
Can you do it in a structured manner?
Well, you're full of chunks and stuff, it gets to be tricky when you have it.
Yeah, this is spaghetti code, totally.
Yeah.
And yes, you can do assembly language in a structured manner, but you have to. It's kind of like structured AppleSoft. You have to impose discipline on the unstructuredness.
As an aside, I actually tried the ideas I did in structured AppleSoft to put them into assembly language, and it just made assembly language no fun. It just didn't bring It's like, and the whole thing about assembly language is that it's raw speed. In AppleSoft, I don't mind the inefficiency because it's already inefficient.
Right.
In assembly, I do.
All right.
You can do anything about the asset.
Right. Okay. We have to fix that @ sign thing. So I said earlier, we didn't know exactly where we wanted to go. Well, now we know where we wanted to go. We wanted to go to line L. The X command will scan backwards from the place you specified, find a branch to star, and fix it. So you can do forward branches really easily, kind of as you're going along, having to.
As long as you don't do more than one at a time.
As long as they are properly nested.
This is a language with no more than 26 commands, right?
On the screen?
Yeah.
Yeah. But you can go on to the second screen.
Just reassign it.
So now the branch is fixed. So if the A register is 0, we're going to branch to 2000A, and it's going to print it out, and then go back. Aha. Okay. So we're doing good.
Couple vowels.
Let's see, what else can I show you? Well, it'd be nicer if it was inverse instead of normal text. So I think if we strip off a couple bits, we can print it out in inverse. So before we call cout, we're going to modify the value of the A register. Now if I go and insert at line L, what it's going to do is push all of this stuff down, and it's going to adjust this branch to point down there. But the stuff I want to insert, actually, I want the branch to go to the stuff I'm going to insert. So there's a slight variation on the insert command called open that will push all this stuff down, but references to the beginning of it will just stay references to the beginning. So you're kind of inserting something at the beginning of the target branch. So instead of I, I'm going to O. So now you'll notice that branch did not change. If we do a binary AND, FF would just do nothing. 3F will strip off the 2 high bits. And close up the space. What's that M about?
That's your inverse carriage return.
D becomes 0.
Inverse carriage return. Damn it.
Law of unintended
You're in
consequences.
Super-Mon, you can fix it.
Say again?
You're in Super-Mon.
Super-Mon, yeah, you can fix it. So I need to insert some more code. So
8D begins 0D.
8D, 3F. It's going to end up 0D, right? No. I don't want to print out a character. If I just load the A register,
Well, you could always put the bit back if it's 50.
Yeah.
oh, sure. That'll do it, right?
Yeah, you don't even need to be any.
Oh, right. No, yeah, you do.
You do.
Otherwise, it'll always put the bit back.
Oh, yeah.
We still want inverse text.
Right.
I noticed I got some cruft left over from my previous commands. If you just give it a single address to the kill or a range, it will do full statements. All right, and we've got a branch to fix.
What's the asterisk next to the P?
That's telling you the next. So if you go and assemble some more code right now, that's where it will go.
Got it.
So we've got to fix that branch. All right, so we're in business. So, that's a brief tour of the features of Super-Mon.
How about saving this great work?
Pardon?
How about saving this great work?
Oh, yeah. So, as I mentioned, Super-Mon's integrated with Naked DOS. So I happen to already have a file called ftests, a label called ftests, which is df01, or df10, sorry. So as I showed yesterday, you could do I'm saving a lot more space than I really need to. I'm saving, everything from 2000 to 365. A couple things happened here. So first of all, I saved the file with the right command. Super-Mon noticed that I was saving the program area that I defined earlier, and so assumed that it would also be a good idea to save the symbol table at this point because I have changed the symbol table. But if I save some other area of memory that's unrelated to the program, it won't do that. So there's our file. It's 20 sectors long and at the bottom. For convenience, because it knows about the program area, I can just say I can leave out the address range entirely and say I want to write to file ftests, and it will assume the program area. So that's a handy way to save your code. Likewise, if you want to read some code, so the zap command will clear out the whole area of memory. Code is gone. If you don't specify an address to read, it will assume the program area, and it will read the symbol table.
What happens if your program area is smaller than the file you're loading? Say you only get
It will just keep it always. Naked DOS always reads the whole file.
So there's now, but you said Super-Mon is no longer dependent on DOS 3.3. Can it still be used in a DOS 3.3 environment, or does it have to be used in Naked DOS?
It can kind of be used in a DOS 3.3 environment. As long as you don't want to use disk commands, it's perfectly happy to sit up there in the ROM space with DOS down below.
You mean use this command from within here, from within Super-Mon? It doesn't kill DOS.
It doesn't kill DOS, exactly.
Right, so you could go ahead and write some code in 2000 and then desave it if you want to.
Yeah.
Can you desave the symbol table too? Not easily because it's
Not easily.
Right.
Yeah, because the symbol table's in the D1000 space.
Right, so you'd have the bank switch to get it.
And it uses the D1000 space is actually there's two of them,
Right.
and you'd have to switch back and forth to save it. It'd be a pain in the ass.
All right, but you could write something.
You
If
totally
you didn't care about the
could
symbol
write a whole bunch of
table, you
code.
could go ahead, code in DOS 3.3 and desave it, but not ProDOS.
Not ProDOS, because ProDOS wants the language space.
Right.
And some, the idea has come up, well, put ProDOS over in the alternate thing.
Well, could Super-Mon live in the alternate thing?
Or something like that. That's a lot of
Yes.
Um,
So do you live in Super-Mon and Naked Dots now? Is that like your primary environment?
yes. I like it.
He's created his own little world.
I was gonna say, if you make your own tools, you're probably gonna use them.
Well, that's what we're doing here. We get to spend this week in our own little world. and when all the Bible-toting teenagers showed up yesterday, I felt kind of violated. I'm like, no, the outside world can't come in yet.
Well, that's their own little world. You know what I mean?
Exactly.
Their world is our world.
I'd rather have a whole lot
You just bounce off the edges and don't really get involved.
But I think, one of the speakers, maybe it was the keynote, mentioned that the wonderful thing about the Apple II, when I got it, I was like, wow, I can make a whole world in there, and it's my personal playground.
What happens if you do an insert and it pushes 32 bytes down and it takes some branches past the 27 byte boundary?
It will beep. It will print out the address of the offending branch, and it will not adjust that branch, which means you've got some work to do to tighten stuff up and
Well,
fix
that's
that
fine.
branch.
That's perfect.
The last thing I wanted to do, I think I've got a couple minutes, is let you hear what Naked Dots sounds like when it's doing stuff. Because the track-to-track speed is nice. So first let's write a big file. Let's write as much memory as we can. Let's see if that tests.
That's a lot of memory.
So that's a lot of memory. Let's see if this works. Didn't like that.
Access already exists, is that the issue?
So that's the track write speed. And that's the track read speed. So that's what Naked Dots. That's what Naked Dots sounds like. You'll notice if you run it on a real Apple II that the seek from like to the end of the disk or back sounds different because I didn't put in the fancy acceleration and deceleration stuff that Wozniak put in his seek routine. So my seek's a little dumber, a little slower, and sounds kind of funny. Virtual 2 doesn't quite know what to make of my disk seeks, and it makes the wrong noise. Like if
Send
you
them a
just,
bug report.
if you just seek from track 5 to track 0, it'll make a noise like you just came from the end of the disk back to track 0. But I might have some things. But I wish he'd open source it and then I'd fix it myself. Any other questions?
Can you talk a little more about how the symbol table is stored?
How the symbol table is stored?
Yeah.
Sure.
Assuming you take some assumptions about writing that out as hidden metadata or what?
Well, you can certainly dump it. So here's the symbol table for all of memory. So you could print that out to a text file.
And you get the public API symbol table, the hooks for free. Those labels are automatic.
Yeah,
The stuff that's in the reference manual is already there.
it's already there. In addition to a bunch of the soft switches in the C100 area, so probably several gigabytes there. So that's probably the easiest way to export the symbol table, and then to import it, you could edit this, flip them around, say.
I mean, when you save a program
paste them
area.
into an emulator.
But when you save a program area, it scans that area for symbols that it knows about and automatically saves those with it.
It actually just saves the entire symbol table,
Oh, okay.
regardless of whether those addresses are inside or outside, because your program will often reference reference things
Right.
outside of its own space.
Okay.
So if you're starting a new program, do you have to manually delete any symbols that you defined for your previous program?
Yes. So, like, the exclamation point operator will delete all the symbols from F800 to F800 and list them out. So now if you list F800, it doesn't know where plot is anymore. Now we got the symbol table back.
What do you just do?
I just reloaded it.
Oh,
Can you
Where was I going? Oh, you wanted the structure of the symbol table. It's really compressed. Each symbol occupies 5 bytes on one part of the language card bank and 5 bytes on the other part, so 10 bytes total. Wow. So 8 kbytes over 10 is about 800 symbols that you can store in Super-Mon, which is plenty for the big game that I hope to write someday before I die.
You'll do it, Mark.
And symbols can be 1 to 8 characters if you use numbers, 1 to 9 characters if you use only letters. So 9 character labels are a lot nicer than 8. You can actually kind of spell a few more things out.
I may have missed something, but you can protect areas of memory from being overwritten, or you get constantly in danger of overriding them if you forget what they are.
Very much danger, which is also part of the fun, actually.
I see.
You know, it's like playing a computer game. If you don't save often, you are likely to die.
But that's when you go to sleep at 3 o'clock in the morning. Get up and reload the last one you had.
Any other questions?